Okay, so welcome back everyone to the Reading Club. And in today's episode, we are going to continue our discussions on pre-solve reductions. Right, so this is the second part of the pre-solve discussions. In the first part, we covered a few basic things, right? So we are looking at one constraint at a time reductions, and we covered some basic cleaning and bound strengthening and coefficient strengthening, right? So we covered this three pre-solved rules in our first video, and we are still looking at one constraint at a time, right? So in today's episode, we are going to continue our discussion. We are still going to stick to one constraint at a time, but we will see more stuff, and hopefully it will be more useful, right? So these are very basic things, and they were covered in the first part, and if you haven't watched that first part, I would recommend you watch them first, because otherwise it will be like harder to follow this part. So the link for that video should be in the description. And now let's focus on more pre-solved rules that look at one constraint at a time. Okay, so we looked at coefficient strengthening, right, in the previous video, which was we have AIX, let's say this is greater or equal to BI, right, and we want to modify the coefficient AI, right? So we could only do this when at least something in our X, some variables in our inequality are integer variables. Okay, so if all of these are continuous variables, there is not much we can change on the coefficient side. So we'll focus on at least something is integer. Right. So for now, we will even go even a step further, right? So let's say all of them are integer, right? So in other words, support of AI, right? So all the coefficients which are non-zero in this equation, right? So those indices are subset of or all integer indices, right? So all of these x variables are integer for now, and we are going to do Chvatal Gomory style tricks, right? So what exactly we are going to do? So first of all, we can so this left hand side part is bigger than the right hand side part, right? So we can always generate valid inequality by rounding up the coefficients, right? So this is still greater or equal to BI. So for now, we are also going to assume that all of our variables have finite upper bound and their lower bounds is equal to 0. So if this is not the case, the lower bounds are not 0, then we can always shift our variable so that their lower bounds will be equal to 0. Okay, so what did I do over here? I just sealed the coefficients. I just increased the value of these coefficients, and this is still valid because it was before it was on the bigger side, and it is still on the bigger side. We are just adding more stuff on the bigger side, which is still a valid inequality, right? And we said that all of our x variables are integer. So this is integer, this is integer, right? So this is the largest, so the next large integer value for a coefficient, right? So this is integer, this is integer. So since everything on the left hand side is integer, we can even round up the right hand side, right? So if this entire stuff is greater or equal to 3.5, then we can also say that it is not just greater or equal to 3.5, it is actually greater or equal to 4, right? That's a very easy thing to do, right? So let's remove that. We are basically going to round them. So just because, so this is still a valid inequality, but can we use this instead of this one, right? We don't know. So when can we use it? When this one is dominating this inequality, right? So recall the definition of dominating inequalities. Basically it says that the feasible points in this inequalities, right, they are basically a superset of the feasible points over on this inequality, right? So every point that satisfies this one should also satisfy this one. If that happens, then and only then we can do this. So this one will be a stronger inequality, and that's when we can substitute it. So we just rounded stuff, and we don't know whether it is actually the case. So we'll see. But let's say this is not the case, and so we can actually do little bit more than giving up over here. What we can do is just we can multiply both sides by a scalar s, right, before rounding. So what will happen on the left hand side is AIS, and then we round it, right, x, and here also we multiply BIS, right. So after multiplying, then we round it, right. So this is basically same thing as I'll just multiply s on both sides and apply the same logic that I had before. So this, what is the point of doing this multiplication by s is that sometimes just normal rounding without multiplying by this s may not result in a dominating inequality, but for some s value it might be the case, right. So that's what we are looking for. Okay, so now let's address the dominating part, right. So let's first of all make all the right hand side equal to 1. So we will have our left hand side, which will be AI by BI times x is greater or equal to 1. Okay, over here it will be AI s, it's a seal value divided by BIS and its seal value, right. All of this is greater or equal to 1. Now if let's say all of this okay, I forgot to multiply this by x, so let's say this is multiplied by x and this is greater or equal to 1. Okay, so the coefficient of x here is AI by BI, here it is AIS by BIS, both of them sealed. Okay, so which one is stronger, right. So we are both greater or equal to 1, right. So whichever one has smaller coefficient is obviously going to be a stronger inequality, right. So anything, if I have, let's say, all of my coefficients over in this inequality are smaller than all the individual coefficients for these inequalities, right. So in that case we can say that all the solutions that we will have, all the x values that will satisfy this one will always obviously satisfy this one, and there will be some more x values which will satisfy this one, right. So what I'm trying to say is that for any individual coefficient we will have AI k, let's say, or let's say let's use another index, right. So AI, let's say j times s, right. So this part, and we are going to seal them, and this is the denominator, which is BIS, we are going to seal them, right. So this has to be less than equal to AIJ by BI, right. So this should be true for all j, all the variables in this inequality. So if this is true, that's one condition, right. And so this is kind of good, but at least there should be some j or some k, right, for which this inequality is strict, right. So if that happens, then we know that this inequality is strictly dominating then compared to this one, right. So this dominates this inequality. So if this happens, right, so all of my coefficients are smaller than their corresponding coefficients in this equation, and they're both right hand sides are 1, right. So this is the goal, right. So this is what we want to find. So we want to find an s such that this happens, right. So what all s we can try? How do we find this s value? The answer is not known, right. So we don't know how to find this s value, so we give up. Actually we don't give up, we just simply try a bunch of random s values, right. So what Gurobi tries is this values, right. So they try s equal to 1, right, so which is basically this inequality, right. So let's say we are looking s equal to what, and so first they try s equal to 1, then they find out what is the biggest coefficient, right. So let's just call it what is the biggest absolute coefficient in this equation. Let's just call it a max, right. So they try 1 over a max. Let's say the smallest absolute coefficient is a min, then they try 1 over a min. Okay, what else do they try? They try something more, which is 2t minus 1 by 2 times a min, right? So this is also something they try for t equal to 1 to 5. Okay, here also it is like not just 1 over mx, it's then 1 over mx, 2 over mx, so it's basically again like t over mx. Here also it is t over a min, right? So these are the set of values they try, right? So 1 is over here, 5 values of this type, 5 values of this type, and 5 values of this type. They are all different, right? So this is basically like 1 over 2 a min, then like 3 by 4 a min, and things like that, right? No, it's not 3 by 4, it's still 3 by 2, 5 by 2, 7 by 2, and so on and so forth. Those values they try, and they just hope that one of them will result in a dominating inequality than this one. So that's what they try, and it's been working for them. Actually, it's this particular Presolve rule is kind of applicable on a lot of models, but its effect is not very high, right? So it brings basically in terms of time absolutely no improvement. In terms of nodes, it brings some improvement. It like 4% improvement in terms of node when we look at instances that are solved that basically take at least 10 seconds to solve, right? So 4% in nodes. So this is basically saying that it is either not able to find a lot of this kind of inequalities, or even if we strengthen it by using this kind of things, it is not really changing much, right? So the resulting LPs are still equally hard to solve. They're not significantly tighter, or so on and so forth, right? But anyways, like we have something in our plate we can improve, right? So we can try to maybe find some better values of S, or maybe find some way to quickly find out which S values will work better for us, and then directly use them, or maybe can completely drop this, right? So that's the preprocessor, and now let's discuss the other ones. Okay, so for this one, let's start with an example. Let's say we have x1 minus 3x2 plus 6x3 equal to 9, right? Let's say all of these x variables are integer. Okay, what can we deduce about x1 using this equation is that this term is multiple of 3, this term is multiple of is basically multiple of 3, and this term is also multiple of 3. That means that x1 should also be a multiple of 3. So we can substitute x1 equal to 3z, and then when we substitute it here, then we can divide this entire equation by 3. Then we have z minus x2 plus 2x3 equal to 3. Okay, so this is the kind of reduction that we want to do. Okay, so first of all, what all things we need for this kind of reductions? So we notice that all the coefficients over here are integer, all the variables are integer, and b also happens to be an integer, or everything has to be an integer, right? And then we find out the GCD of some things, and then deduce things based on that, right? So let's try to formalize all this process. So first of all, not everything is going to be integer. So for that, we are going to find the GCD, greatest common divisor of what? Of all the coefficient, right? So a1, a2, and an, right? So these are my coefficients in my constraint, right? So I find the GCD, right? So you might know that how to find GCD using Euclidean algorithm for all this all the integer values, but you can actually use this Euclidean algorithm for finding GCD of all the rationals also, right? So these are rational numbers Q, right? So these are not necessarily integer numbers, but the GCD D, right? So this is these are basically rational numbers. And how do we define GCD? is that each individual ai by d, this should be integer, right? So we want to find the greatest common divisor so that this happens for all I, right? Now you can use Euclidean algorithm, but in the paper they used they basically also discuss some tricks to avoid numerical difficulties. Okay, so we are not really going to discuss those specific parts, but that's the idea, right? So that's the idea. What we want to do is that all the coefficients are rational numbers. We first of all convert everything into integers, and then we find the GCD of all the coefficients, right? So all of these coefficients, we have GCD, and then we divide everything by this GCD, right? And let's say if the entire left hand side is divisible by certain number, let's say 3 or 5 or something, but the right hand side is not divisible by that same number, then we know that this entire equation is never going to be satisfied because it's an equality constraint, right? So this is infeasible. So we can basically detect some infeasibilities just by doing this GCD computations sometimes, okay? Not always. But we did something different when we did this kind of reduction over here, right? So what we did was we basically computed the GCD of all the numbers except one number. Okay, so we did the GCD of A2 up to AN, which is 3. These two numbers, and it so happens that 3 also divides 9, right? So 3 is 9 is basically a multiple of 3. So in that case, we could deduce that x1 should also be a multiple of z and multiple of 3, and then we could basically do this substitution. But what happens if we have some other number than 9? Let's say 8 or 7 or something like that. What can we do? Right? So there is still something that we can do. Right? So this is not infeasible because entire left hand side is not divisible by 3, because this x1 is it's just hanging, right? So we can't really do that, but we can still do some things about it, right? So there we use some number theory. Okay, so let's see what that is. Okay, so it's a concept called modular inverse. Okay, so when we divide everything by GCD, right, so we basically make them like very small coefficients, and those coefficients now are relatively primes, right? So basically what I mean to see is that if we have a1, a2 and so on, all the numbers, right, once you divide them by their greatest common divisor GCD, then if you try to compute the GCD of this entire thing, right, so this has to be equal to 1, right? So these are basically relatively primes. Okay, so that is kind of important for our task. Okay, now what we want to do is this, we said that in our equation, right, so we have first term x1 and a lot of other terms for which we computed a GCD, which is d, and there is some right hand side value which is b. Okay, and we are specifically looking at the case where this d is not dividing this b part, right? So it is leaving some remainder on this b part. All of these are strictly divisible by d, and this part is also not divisible by d. Okay, whatever coefficient of x1, coefficient of, let's say we'll call it a1 x1, right? So this is not divisible by d, right? So this is since this is an equality, right, so we can say that whatever remainder b leaves when we divide it by d, the same remainder should be left on this entire term a1 x1. Okay, so in other words, we can say that this equation is we can say that a1 x1 is congruent to b mod d, right? And the condition here is that this a1 should be relatively prime with d. So basically GCD of a1d should be equal to 1. okay, which is obviously the case. So here normally if this would have been an equality, we would just say that x1 equal to b by a1, and we will have something about x1. But here when we talk about this modular arithmetic, we have modular inverses, right? So we have a1 inverse b. So what is this? This is also an integer. Okay, so this is an integer. It is a special type of integer. So what is an modular inverse of a1? So it's basically defined as this thing, that a1 times a1 inverse. This is not a fractional number. This is also an integer number. But when you multiply it by its inverse, then it leaves the remainder 1 mod d. Right? So this, like, find an integer number mod d, so that when you multiply that number with a1, it leaves that remainder 1, right? So we want to find that number which is strictly less than equal to d. Okay, so this is what we have. x1 is congruent to a1 inverse mod d, right? So how we can find it, it's kind of a bit number theory kind of stuff, so I'm not really going to discuss all of that. It's also not even discussed in the paper, but it's kind of, you can just assume that it is given a number and its relative prime, it is possible to find its modular inverse. Okay, so this is what we have. So what does this mean? That x1 leaves this remainder a1 inverse b when you divide it by d. So we can basically substitute x1 equal to d times z plus this number, right? And this number, you basically reduce it down to the remainder part actually. When you also, this number also, you divide it, keep dividing it by d till you hit the remainder. So this is basically a1 inverse b, right? So the smallest number which leaves the same remainder as this one when you divide it by d. Okay, so this is what we are going to substitute x1 with. So let's actually take a look at an example so that it becomes slightly more clear. Okay, so this example is again in the paper, which is minimize x1 plus x2, so that the coefficients are kind of a bit scary, but don't worry about that. 1867 x1 plus 1913 x2 equal to, this is a very big number, 3618894. Okay, and x1 x2 are both greater or equal to 0, and they are both integers. Okay, now this is a prime number, this is also a prime number, and this is some number, let's say this is some big number. Okay, so let's try to do what we did before, right? So let's use this, let's say this number as d, right? So this number is not divisible by d, this number is divisible by d, and this number leaves some remainder when you divide it by d. Okay, so first of all, what we basically did was, let me write it down here. We had x1 equal to d times z plus the remainder part. What was the remainder part? It was a1 inverse times b, right? So this is what we want to do, right? So let's first of all compute, this is our a1 in here, right? So let's compute a1 inverse. So for if you take d as 1913, this is the prime number. In that case, we can say that 1867 inverse is same as 1206, right? Mod this number, mod 1913. Okay, so basically it says that if you multiply 1206 by 1867, then whatever number you get, large number, right, then you divide it by d, then you will have the remainder 1. Okay, so that's the idea behind the inverses. So this number, we are going to multiply it with b, right? So this is 1206, we are going to multiply 1206 by this big number, and we can say that 1206 times this big number, which is 361 and 8894, is congruent to what number? It actually leaves the remainder 1009, right, when you divide it by 1930, right? So this entire part is 1009. Okay, so we know D, we know this number, so we can now substitute our x1, right? So our x1 is equal to 1913 z, some multiple of z plus some remainder it leaves, which is 1009. So we know that x is this type of a number based on this equation, just by using this equation. Okay, this basically reduces down the choices of x by a huge margin. Okay, so when we substitute this thing over here and divide everything by 1913, so this one obviously goes away. But let's say divide everything by 1913. Okay, what are we left with, right? So when we substitute everything over here with z, let's see, it's a big number actually. Let's see, so this big number is 3571571 z, this is z, not 2, plus 1913 x2 equal to 1735091. This big numbers, okay, but like the good part is that everything now is divisible by this 1913, because we substituted it that way, so that whatever remainder was left by this term, it's also kind of left by this term, so that now when we substitute everything, it's kind of divisible by 1913, right? So when we divide everything by 1913, what do we get is 1867 z plus this is 1, so x2 equal to 907. Okay, so this is a very simple equation to solve, right? So here also we can say that z is greater or equal to 0, right? So white is very easy to solve, and z is also integer, right? So now if z equal to 1, this term is it's never going to satisfy, because this is bigger than 907 and x2 is positive, non-negative. So z has to be equal to 0. Any positive number in z will just violate this equation. So z is equal to 0, and if z is equal to 0, then we can say that x2 equal to 907, and yeah, that's it. We basically solved it for x2, then we can substitute it for x1, or we can say that z equal to 0, put it in this equation, so we can have our x1 equal to 1009. Right, so this is the only solution and the optimal solution for this problem, right? And so Gurobi basically solved it in the pre-solve reduction case, right? So right at the root node. But if we do not have this pre-solve rule, right, if we cannot substitute x1 by this number, then it takes over 2000 nodes, branch and bound nodes, to solve this problem. Okay, so this is sometimes very, very fast, other times it's not super fast. It's a lot of times it is not even applicable, because all the coefficients of this integer variables has to be different and everything, so it's kind of hard. But whenever it is applicable, it is very, very fast, right? So that's this Euclidean stuff, Euclidean and modular inverse reductions, and overall it leads to about like 3% improvement in time, right? So we saw that it solved this entire complex example in like no time, just by doing all this computation. You might feel that these are very large numbers, and so by hand these computations are kind of tedious to do, but the computers can do all those multiplications and computations very, very fast, right? So it is not at all hard for a computer to find modular inverse, and there are algorithms for that. There are finding remainder is like very trivial for computers. So all of these are very trivial operations that I just demonstrated. Okay. Okay, so the next we are going to see is simple probing. Okay, so let's take a look at an example, which is 10x1 plus x2 plus x3 and so on and so forth, all the way up to x11, right? All of this is equal to 10. Okay, so this is again like the example which is given in the paper, and x1 is binary, right? So it's between 0 and 1, and all of these other variables are not binary, but they are all xj is less than equal to 1 and greater equal to 0. Okay, so what can we deduce on using this equation? So it's kind of simple, right? So when x1 equal to 1, right, so this part will be 10 and this part is 10. So x2 to x11, all of them are 0, right? So when x1 equal to 1, all of these other variables are 0. What happens when x1 equal to 0? So this is 0, right? So this part is 10 and there are exactly 10 individual variables left, right? 2 to 11, and they all of them have to be at their upper bound to satisfy this number, right? To reach this number. So all of these numbers in this case will be equal to 1, right? So here we can simply substitute xj equal to 1 minus x1, right? So they were not even first of all integers, but now they are integers and they are basically 1 minus x1. Okay, so that's the reduction. It's kind of easy to do, but all of this process that I just did, it can be actually very formalized also, right? The problem I'm not really going to describe is because it doesn't really have a lot of effect. It's basically, this is something like, you know, taking one branch and taking other branch, and it's kind of probing, right? And it doesn't have a lot of effect, this particular Presolve rule, because in the MIP solver we can do actual probing. Okay, so there is an actual probing which is not just probing on one constraint, but it's kind of you know, probing on entire LPs. So because of that probing, even if we just disable this individual constraint probing, it doesn't have a lot of effect. But yeah, it's there, right? So I'm not really going to discuss how to do it, but you can basically figure it out. You can find out what is the infimum of left hand side, what is the supremum of left hand side, and see how it relates to this b value. And so this kind of things mostly happens when we use some sort of big M constraints, right? So we basically look for variables such that their coefficient is basically equal to the supremum of this constraint minus b, right? So supremum of this part is 20 and b here is 10. So supremum minus b is 10 and it is exactly the coefficient of this variable. So this is basically a super large coefficient, which normally happens in big M type of constraints. So we detect them and remove them, right? So not really remove them, but we fix a bunch of other variables, right? So all of these variables are now fixed to 1 minus x1. So we only have one variable left over here. Okay, so that's the preprocessor, and there is one more. It's called SOS reductions, but I'm not even SOS. There are 1 and 2. There are 2 types of SOS constraint. This is basically like exactly one of this variable can take non-zero value. Only one of SOS one set can be not equal to 0, right? If there is basically a set of variables which is called SOS1, and same for SOS2 is like this is a set of variables, so that exactly 2 of them, this is not only, this is exactly exactly two of them can be non-zero, and they have to be consecutive, right? So this is like an ordered set, special ordered set, right? So, and you can do basically some so this is 1, this is 2, and so on. So for this specific order, if there are two of them that are non-zero, then they have to be next to each other. Okay, so because basically we can do bunch of Presolve reductions on this type of constraints, but they are not very frequent, and that's what they said in the paper, and the reductions are very trivial, so I'm not really going to describe them in this video. Okay, so that basically concludes everything that we wanted to discuss about reductions using one constraint at a time, right? And next we will look at multiple constraint at a time in the next part. Okay, so in this video, what all things we discussed? We discussed some coefficient strengthening using Chvatal Gomory type of strengthening. Then we did some Euclidean algebra to do more strengthening, and this one was probing, and SOS we did not discuss, right? So this one we did not discuss, but it's kind of not so hard to, it's not super important as well, I think. So yeah, that's the end of this video. So keep an eye out for the next part, in which we will discuss multiple constraints at a time. Meanwhile, if you liked everything that I discussed, if you understood some things, or if you didn't understand but you just gained some information, hit the like button and subscribe for more videos. Okay, so thank you, bye.